All right, let's dive right into this explainer. If you've ever looked up at the night sky and wondered what's truly holding everything together, planets, stars, galaxies, the whole shebang, you are in exactly the right place. Today, we're unpacking the core mechanics of Einstein's general relativity. We're going to fundamentally shift our perspective, looking past that everyday illusion of gravity as some simple magnet-like tug, and instead explore the mind-bending geometric reality of the universe itself.
Space-time tells matter how to move, and matter tells space-time how to curve. You know this famous quote by the brilliant physicist John Wheeler? It's just the ultimate paradigm shift. It perfectly encapsulates the entire engine of general relativity in one single sentence. It's this elegant dynamic loop, right? Matter creates the geometry of the universe, and in turn, that very geometry dictates how matter moves through it. It's a continuous cosmic dance.
Section 1. Gravity as space-time curvature.
To truly grasp this concept, we first have to completely dismantle that old Newtonian idea. For centuries, we pictured space and time as this rigid, unchanging framework, basically a static stage, where gravity acted instantly across huge distances, like some invisible tether. Well, Einstein proved that stage isn't static at all. Space and time are actually woven together into a single, flexible fabric. So instead of an invisible pulling force, imagine space-time as a giant, stretched-out rubber sheet. When a massive body, like a star or a planet, sits in this space, it sinks into the sheet and creates a dynamic deformation. Objects moving nearby aren't being pulled by some mysterious force. They're simply following the natural, inward-sloping curves of this unified fabric. Gravity isn't a pull, it is literally the shape of space itself.
Section 2. The equivalence principles. Now, let's see how this incredible geometric concept builds on Einstein's profound realization that gravity and acceleration are, practically speaking, completely indistinguishable from one another. The weak equivalence principle on the left here accepts what we've long observed, that inertial mass perfectly equals gravitational mass. It's exactly why a feather and a hammer fall at the exact same rate in a vacuum. But Einstein takes this a step further with the strong equivalence principle. He states that locally, gravity entirely disappears. Imagine being in a plummeting elevator in a severed shaft. For you, in free fall, the effects of gravity simply vanish. You float. This creates a local inertial frame that perfectly mimics the flat, gravity-free space of special relativity.
Section 3. Geodesics and curved paths. So this brings up a massive question. If gravity is essentially just geometry, how do things actually move through this locally flat yet globally warped universe? Well, they follow a geodesic. By definition, a geodesic is the natural straight-line trajectory of a freely falling particle, generalized into a curved path in space-time. If you aren't being acted on by external forces, like the thrust of a rocket or just the friction of the ground pushing up against your feet, you're traveling along one of these fundamental paths. In math terms, you're parallel transporting your own tangent vector along the curve of the universe. But simply put, you are coasting forward in what your body feels is a perfectly straight line, even if the space around you is bending. It's essentially the cosmos's version of coasting.
We can get an intuitive feel for how curvature dictates motion by looking at something called geodesic deviation. Picture some ants crawling on 3 different surfaces. On a totally flat surface, the ants' initially parallel paths just remain perfectly parallel forever. Simple enough, right? But put those ants on a spherical surface with positive curvature, and their straight-line paths naturally converge. Switch to a saddle shape with negative curvature, and they diverge. The crucial takeaway here is that there's no force pushing or pulling these ants together or apart. It is literally just the geometry of the surface they're walking on. Taking that spherical shape a bit further, just look at lines of longitude. They start out completely parallel at the equator, but they inevitably converge up at the North Pole. The acceleration of this deviation between neighboring paths is the true, measurable signature of a non-uniform tidal gravitational field. And why does this matter? Well, this convergence is the exact, measurable proof that we're in a true gravitational field, not just accelerating in some rocket ship. A completely uniform gravitational field wouldn't cause these paths to converge or diverge. Only the tidal variations caused by actual space-time curvature reveal that a massive body is present. Section 4. The mathematics of spacetime.
To accurately map this complex geometry across the vast cosmos, physicists obviously can't just use standard high school algebra. They need a very specific mathematical toolbox. Okay, prepare to have your brain slightly broken for a second. 7.41 times 10 to the negative 28 meters. In the world of general relativity, physicists simplify their equations using geometrized units, setting the speed of light and the gravitational constant to exactly 1. When you do that, time is measured in meters, and incredibly, masses too. So that microscopic fraction of a meter, That is the literal geometric length of one single kilogram of mass. Wild, right?
Beyond those mind-bending units, scientists use a heavy lifting toolkit to measure all this. The mathematical toolbox includes Riemannian manifolds, which give us a flexible canvas, continuous spaces that are locally flat, perfectly accommodating that equivalence principle we talked about. Then you've got tangent vectors and one-forms, pointing the way, defining directions and rates of change. And finally, tensors. The metric tensor acts as the ultimate cosmic ruler to measure distance in curved space, while the Riemann-Christophobal tensor describes the exact nature of that curvature. These advanced mathematical tools are what allow scientists to stitch together those locally flat frames and calculate precise changes across the universe.
Section 5. Detecting Space-Time Ripples.
Okay, so how do we actually apply this incredible mathematical and conceptual framework to modern astrophysics? Basically, how do we measure actual ripples in this curvature? We know that stationary mass curves space, but what happens when massive objects violently accelerate? They create gravitational waves, literally ripples in the fabric of space-time itself, propagating outward at the exact speed of light. And the secret to detecting them goes right back to those ants converging on the sphere. By measuring precise geodesic deviation, meaning the unimaginably tiny changes in the proper distance between freely falling test particles inside a detector right here on Earth, we can actually catch these elusive ripples as they wash over our planet.
I want to leave you with this final thought on the sheer scale of the cosmos. To put things into perspective, the Earth's gravitational field is actually relatively weak. Its gentle space-time radius of curvature is a massive 200 billion meters. It barely bends the local geometry. But consider this. What kind of extreme, violent space-time ripples are produced by the cataclysmic collision of incredibly dense objects, like neutron stars or massive black holes? The sheer energy required to violently shake the fabric of the universe is staggering to think about. And honestly, thinking about that scale perfectly sets the stage for our next explainer, where we'll dive into the exact astrophysical sources that create these gravitational waves. Until then, keep looking up and keep questioning the very shape of the reality around you.